Welcome back. Today, we're going to dig a little deeper into the world of feature selection and uncover why filter methods, while useful, aren't always the full story. Last time, we explored filter methods for feature selection. Think chi-square tests, correlation coefficients, or ANOVA. These are classic statistical tools that help us quickly assess which features might be relevant to our target variable. These methods are fast and simple, evaluating each feature individually against the target variable. They're like a first pass, giving us a quick sense of what might matter. You score, rank, and pick the top features, like sorting clothes by appearance, not by how they work together. It's efficient, but it's also a bit superficial. The main advantage? Speed. No model training required, so they scale to huge datasets. You can process thousands of features in seconds, making them ideal for initial data exploration. They're perfect for quickly dropping features with zero correlation to your target, reducing noise and making later steps easier. This helps streamline your data and focus your attention. But here's the catch. Filter methods ignore feature interactions. They don't consider how features might work together to influence the outcome. A feature might seem useless alone, but could be powerful in combination with another. Sometimes the magic only happens when features are paired or grouped. For example, wind speed and cloud cover might not predict rain individually, but together they're strong indicators. This is a classic case of feature interaction that filter methods miss. Filter methods miss these interactions entirely. They can overlook subtle but important relationships hidden in your data. That's why we need more advanced techniques. Methods that evaluate groups of features together, capturing those hidden patterns and synergies. Like trying on a full outfit, not just individual pieces. The whole can be greater than the sum of its parts. Relying only on filter methods can mean missing out on valuable information. You might accidentally discard features that are crucial when combined with others. To build robust, accurate models, we need smarter feature selection. It's about finding the right mix, not just the right ingredients. So, let's dive into those next. Methods that go beyond filter techniques and help us unlock the true potential of our data. If filter methods are too simple, what's next? Enter wrapper methods. These wrap around a machine learning model, using its performance to decide which features matter. The process: select a subset, train a model, check performance, and repeat with different subsets. It's like an eye doctor testing lenses, comparing combinations to find the best fit. Common strategies include forward selection, add features one by one, and backward elimination, remove features one by one. Wrapper methods are powerful because they test features in real-world scenarios, not just by statistical scores. They're tailored to your chosen model, ensuring practical usefulness. The result? A feature set that's not just statistically significant, but actually boosts your model's accuracy. That's the power of wrapper methods. One standout wrapper method is recursive feature elimination, or RFE. RFE starts by training a model on all features, then removes the least important one. It retrains, reevaluates, and repeats, pruning features step by step until only the best remain. Here's a quick Python example. Python from sklern.datasets import make RFE.ranking. RFE is powerful because it constantly reevaluates feature importance, adapting as features are removed. Wrapper methods shine in accuracy. They find feature sets tailored to your model, considering feature interactions. Unlike filter or embedded methods, wrappers actually use your chosen algorithm to evaluate which features work best together, making their selections highly specific and often more effective for your particular problem. This means you're not just picking features in isolation, but understanding how they work as a team to boost your model's performance. They're flexible. Use any model you like, and the feature selection aligns with your final goal. Whether you're working with decision trees, support vector machines, or neural networks, wrapper methods adapt to your needs, making them a versatile choice for many machine learning tasks. But there's a big downside. Speed. Wrapper methods can be extremely slow, especially as the number of features grows. Each subset tested means training a new model, so with many features, this gets slow, sometimes impractically so. The computational cost rises quickly, and what starts as a promising approach can become a bottleneck in your workflow. For high-dimensional data, wrapper methods can be computationally prohibitive. If you have hundreds or thousands of features, the time and resources required may simply be too much for practical use. There's also a risk of overfitting, finding a feature combo that works perfectly on your training data, but fails on new data. This happens because the method can tailor itself too closely to the quirks of your sample, rather than generalizing well. It's like memorizing answers for one test, but struggling with a new one. Your model may ace the training set, but stumble when faced with real-world data it hasn't seen before. To avoid this, always use cross-validation. This technique helps ensure your feature selection is robust and your model performs well on unseen data, not just the training set. In summary, wrapper methods are accurate and thorough, but slow and potentially prone to overfitting. They offer a powerful way to optimize your model, but require careful consideration of resources and validation. Use them when accuracy is critical and your dataset isn't too large. Otherwise, consider faster alternatives like filter or embedded methods, which may offer a better balance between speed and performance for bigger projects. Is there a middle ground between fast but simple filters and slow but accurate wrappers? Yes, embedded methods. Embedded methods perform feature selection during model training, not before or after. The model itself decides which features matter, often using regularization to penalize complexity. This makes embedded methods much faster than wrappers, but smarter than filters. They capture feature interactions efficiently. Think of a chef adjusting ingredients while cooking, not before or after. Embedded methods are popular because they balance performance and speed, and are less prone to overfitting. Two famous examples: Lasso regression and feature importance from tree-based models like random forest. Let's look at how these work in practice. Embedded methods are often the go-to choice in modern machine learning. Lasso regression is a classic embedded method. It's like linear regression, but with L1 regularization, penalizing large coefficients. This penalty can shrink some coefficients to zero, effectively removing those features. Lasso selects features automatically as it trains. In scikit-learn, just set the alpha parameter to control how many features are kept. After fitting, check 0 means the feature was dropped. Adjust alpha to keep more or fewer features. Lasso is efficient, simple, and powerful for feature selection. Tree-based models like random forest offer another embedded approach. Each tree splits data using the most informative features, and the forest aggregates these choices. After training, you get a feature score for each feature. The higher the score, the more important the feature. This method is intuitive. You build a strong model and get feature rankings as a bonus. In scikit-learn, train a random forest classifier and plot the importances for a clear visual. It's a fast, effective way to understand and select features. Random forest feature importance is a staple in data science projects. Let's break down and compare the three main families of feature selection methods: filter, wrapper, and embedded. Each has its own strengths and weaknesses, and understanding these differences is key to making the right choice for your data science project. Filter methods are fast, simple, and model-independent, making them perfect for quick, first-pass analysis on large datasets. They work by ranking features based on statistical tests, so you can quickly eliminate irrelevant variables. However, they don't consider how features interact with each other, which means you might miss important combinations that could improve your model. Wrapper methods, on the other hand, are much more thorough. They actually test different combinations of features using your chosen model, searching for the set that gives the best performance. This can lead to higher accuracy, but it's computationally expensive and can easily overfit, especially with large datasets or too many features. Embedded methods strike a balance between the two. They select features as part of the model training process itself, capturing feature interactions efficiently and avoiding the heavy computational cost of wrappers. This makes them both practical and powerful for many real-world scenarios. Popular embedded methods include Lasso regression, which shrinks less important features to zero, and random forest, which ranks features by importance as it builds decision trees. In practice, use filter methods for quick data cleanup or when you have huge datasets. Wrappers are best for smaller datasets where you can afford the extra time and want maximum accuracy. Embedded methods are usually the go-to for most real-world problems, offering a great mix of speed and performance. Ultimately, the right choice depends on your data size, the time you have available, and how much you need to optimize for accuracy. There's no universal answer. Remember, there's no one-size-fits-all solution. Choose the method that best fits your project's needs and constraints. For most beginners and even experienced data scientists, embedded methods are often the best starting point, as they provide a good balance of efficiency and accuracy. Now you know how to pick the right tool for the job, making your feature selection process smarter and more effective. Let's put this knowledge into practice and see how it works with real data. Time to get hands-on. Your assignment: use random forest feature importances to analyze a dataset. Find a classification dataset. Try the UCI repository, Kaggle, or scikit-learn's built-in datasets like wine or breast cancer. Load your data, separate features, X, and target, Y. Train a random forest classifier on the data. Extract the attribute. Visualize the importances with a bar plot. Label axes and add a title. Share your results. Post a screenshot. Mention your dataset and discuss which features mattered most. Did anything surprise you? This exercise will cement your understanding of embedded methods. Happy coding!